So we are in continuation with the oscillations and the simple harmonic motion, and our main context of discussion is simple pendulum and its applications. So in simple pendulum and its applications mainly, we have to go through with the concept of simple pendulum, how the energy variations takes place in a simple pendulum, and at what positions we find that amplitude is maximum or minimum, at what positions the kinetic energy and potential energies are maximum and minimum. These facts are to be discussed. Now, one of the very important thing is that simple pendulum is an example of simple harmonic motion. And as we have discussed earlier, that a particle which is executing simple harmonic motion, we find in that particular particle or in harmonic oscillator, we find that as the displacement of the harmonic oscillator increases, the restoring force also increases and their directions are opposite. But whenever we have to take the magnitudes, we normally write F is equal to minus ky, or magnitude will be the modulus of both the numbers. So F is equal to ky. Minus sign we will not take into consideration during the magnitude, because force is basically a vector and the magnitude of vector will be its modulus. So we find that in case of simple pendulum, there is a point of suspension and there is an inextensible thread and it is connected to a pendulum bob. In the mean position or in the equilibrium position, it is exactly straight, it is perpendicular to the point of suspension. Then if a simple force is applied to the pendulum bob, it will begin to move towards the left extreme and the right extreme, or the right extreme and the left extreme. Up to the time it is moving towards any of the two extremes, the displacement will be towards the extreme points, and the restoring force will be towards the equilibrium position or the mean position. And we will find that extreme position, the amplitude of the pendulum bob will be maximum, whereas at the nodal points, we will find that the amplitude of the simple pendulum, that will be minimum. That is, antinodes are the point of maximum displacement, and nodes are the points of minimum displacement. But at mean position, the kinetic energy is maximum, velocity is maximum, but displacement is minimum. And when it goes to the extreme position, we find that displacement is maximum, that is, amplitude is maximum, and kinetic energy totally transforms into potential energy. However, we find that at the extreme position, the velocity will be zero, or velocity, that is, the whole kinetic energy is converted to potential energy, and restoring force becomes maximum, due to which particle starts coming towards the equilibrium position or the mean position. But the total energy of pendulum, that is kinetic energy and the potential energy, this total will remain constant. So these are the various facts we have to explain. So we start with the main concept. So first of all, our discussion is regarding the conditions for the ideal simple pendulum. That is, what is an ideal simple pendulum? So for an ideal simple pendulum, there are certain points to remember. That is, bob must have or a heavy point mass. So bob is supposed to be a point mass. It should be heavy. Then another thing important, suspended by weightless, inextensible, and perfectly flexible string. This is what I have explained earlier, that one end of the string is connected to a rigid point and other end is connected to a spring, that is to a pendulum bob. And we find that the thread or the string, that must be weightless, that we are assuming. However, it is not weightless, and moreover, it should be inextensible and perfectly flexible. Now, medium must be frictionless and non-viscous. So this we are assuming it's a theoretical fact, but practically this is not valid because if we are doing our experiment in vacuum, then we will find that the medium is maximum frictionless and non-viscous. But if the whole experiment is conducted in air medium, we find that the oscillations of the pendulum will damp after some time. So I'm using a term here, damp. So what exactly we mean by damp? There are two types of oscillations, the damped and the undamped oscillations. In damped oscillation, we find that amplitude of the oscillation gradually goes on decreasing and finally it becomes zero and the body comes to the state of rest. And in the undamped oscillations, the amplitude is maintained or amplitude remains constant. Now, point of suspension, as I have just explained, one end of the string is fixed to a rigid support and other end is connected to a pendulum bob. So point of suspension means that this is the point from which the pendulum is suspended. The point of oscillation, this is the center of the mass of pendulum which coincides with the center of mass of the bob, point O. So this will be more clear in the figure, and then we come towards the effective length, the distance from a point on the rigid body to the center of the pendulum bob, that is called the effective length. So the distance between the point of suspension and the point of oscillation is called the effective length of the pendulum. The point of oscillation is basically the mean position. So when the pendulum bob is in the mean position, we apply some force and it begins to move towards the extreme position. So when it moves to the right extreme or the left extreme, we will find that those points will be the antinodes because amplitude will be maximum. And when it comes back to the mean position, that is from where the motion started, that is called the mean position or the equilibrium position where the amplitude is zero. Now we can check this figure. LEFF is indicating the effective length, S is the point of suspension, and there is a pendulum bob as indicated by circle, and O is point of oscillation, that is the mean position. So effective length means the distance between the point of suspension and the point of oscillation is called the effective length of the pendulum. Now, we will find that OA in the figure, OA be the initial position of the pendulum and OP its instantaneous position. When we use this term instantaneous position, we are referring to a particular instant of time when the string makes an angle theta with the vertical. Now weight mg of the bob is acting vertically down and this weight is a force. It can be resolved into two components in two dimensions. One of the component will be mg cos theta and other will be mg sin theta. So weight mg of the bob acting vertically downwards can be resolved into two rectangular components along OP and mg sin theta perpendicular to OP directed towards the mean position. Mean position means the point from where the oscillation started, or it is called the equilibrium position. So mg cos theta is balanced by the tension T in the string. So basically we have resolved mg into two components. One of the component is balanced by tension and other is mg sin theta at 90 degrees to mg cos theta. The restoring force on the bob, F, is minus mg sin theta. When we use the term negative sign, force is towards the mean position and displacement is towards the extreme position. If we take the magnitude of this statement, we have to take the modulus of F and the modulus of minus mg sin theta, and that will become F is equal to mg sin theta. Now for SHM, theta is very small, then sin theta will be theta. So if our assumption is that theta is very small, then in that case, sine theta will be theta or cos theta will be theta. But sine theta is perpendicular over hypotenuse, so it is given by x over L, where x is the displacement from the mean position and L is the length of the string. Generally, we take sine theta equal to theta if theta is less than equal to 15 degrees. Now, in the next thing, we can discuss f is equal to minus mg theta. So, instead of sine theta, we have written as theta because we have proved that if angle is small, then sine theta will be equal to theta. And that is equal to minus mg, and theta is given as x over L. If we wanted to remove the negative sign, it means that we have to take the magnitude, we have to take the modulus of both sides. Then in that case, the equation will become f is equal to mg x over L. You will always remember that modulus of a vector will be its magnitude. So if we take modulus of a vector and if vector is negative, we will find that its modulus will always be positive. So we can again go through with the figure. That is, O is the point of suspension, L is the length, A is a pendulum bob. So that is the mean position or equilibrium position at any instant of time. Suppose pendulum bob reaches to position P. When it is at position P, we find the weight of the pendulum bob is acting vertically down, and that weight is mg. This mg is resolved into two components. One of the component is mg cos theta and other component is mg sin theta. Mg sin theta is from P towards A, whereas mg cos theta balances the tension, and the tension is indicated in the string, that is O to P. So tension at point P can be given by function mg cos theta plus mv square over r. But instead of r, we can take L because the length of the string is assumed to be L. So Tp is equal to mg cos theta plus mv square p by L. What is Vp representing? That is velocity at point P. If A is acceleration, then F is mass into acceleration. Or we can write mass into d square x over dt square. However, we don't require it, so we make it as F is equal to ma. Now from this equation, ma is equal to minus mg x over L. Now m will cancel off from both sides and we will get the value of a, which is negative of g over L into x, and we mark it as equation number 1. Now standard equation of SHM, the acceleration is given by minus omega square x. However, if you wanted to find the velocity, it should be omega x, but now acceleration is minus omega square x. That is second equation. Now comparing 1 and 2, so acceleration is minus g over L into x, and acceleration is also minus omega square x. So we equate the two numbers and eliminating a, we will get the value of omega square. The omega square will be estimated as g by L, or omega will be, that is, under root g over L. Now when we say omega, omega can be written as 2 pi over t, or it is 2 pi n. So we can get the values of time period and the frequency of oscillation from that function. But the basic function is omega square, that is g over L, and omega can be taken as 2 pi over t. Time period t of the pendulum bob is calculated by function t pi 2 pi under root L over g. One of the very important thing to remember that this is the general equation of the time period of oscillation of a pendulum, where g is acceleration due to gravity, L is the length, that is, length means the distance from point of suspension to the center of pendulum bob, and t is the time period, that is time taken to complete one vibration. Sometimes in our question we use seconds pendulum, so we can remember seconds pendulum is that in which time period is 2 seconds, and the length of the seconds pendulum is not exactly 1 meter, but it should be 0.9. However, it is 0.933. 33 is insignificant, so we take the length as 0.9 in approximation. Now, time period is 2 pi under root L by G. Obviously, the time period is independent of mass. In the equation, we don't find that mass is existing. Also, the time period is independent of shape of the pendulum bob, and the material of the bob, and it is also independent of the amplitude of motion, because amplitude will be sometimes less and sometimes more. That is the characterization of an harmonic oscillator. Now, effect of length on the time period, we have to go through that how length is connected to time period. So we can go through with this statement. Time period depends upon L, as T is proportional to square root of L. So if we square the number, it will become T square proportional to L, where L is the distance between the point of suspension and the center of mass of the bob, and is called effective length. So L means effective length, center from the point of suspension to the uh, center of the mass of pendulum bob. So it is indicated in the figure that there is a pendulum bob and it is suspended with a rigid support, and there are S and R 2 points. That is a special case we are dealing, that if we make slight hole in the bottom of the pendulum so that water can trickle down gradually, and it is filled with water as indicated, then what will happen? So we can just make a discussion on this. If a hole is made in the bottom of the hollow sphere full of water, and water comes out slowly, means trickle down through the hole, then T first increases, reaches a maximum value, and then decreases. That is, more time will be taken to complete the vibration, because it is gradually the sphere is getting hollow. So then decrease till becomes equal to its initial value. Now, we can review the figure again. We are finding up to the time it has got significant weight, its time period will be less. But as it is going on, you see, that is maximum value and then decreases till becomes equal to initial value. So, first increases and reaches to maximum value up to the time its weight is more, and when most of the water comes out by trickling, we find that it will become light and it will take vibrations rapidly, so time will reduce. Now, the another part which is important, if a heavy mass M is suspended from a wire of length L and the wire stretched or stretches by delta L means change in length due to elasticity, then find formula for the time period, which is normally written as 2 pi under root L over G. Here we can write this formula as 2 pi under root L plus delta L, that is the change in length, whole divided by G. Then by Young's modulus of elasticity, we know that Y is equal to stress over longitudinal strain. We put the value of stress, that is force over area, and the longitudinal strain as L over delta L. So delta L will come in the numerator. So we will find that mg over L, and A is pi r square, area of cross section, that is pi r square into delta L. So we will calculate from this delta L over L, and that is found to be mg over pi r square y, and its value is calculated to be very, very smaller than 1. And R can be replaced if required by diameter over 2. And if we replace it by diameter over 2, we will find that R square will be D square over 4. And then we can simplify our result. Now, there is a formula for the change in time period over time period, that is delta T by T. This is given by composition half of delta L over L. So it is written as half of, and then for delta L over L, we have computed the value, that is mg over pi r square into y.